So how do I switch? Okay. So this is a screenshot of virtual cell, and most modeling you do with virtual cell or COPASI, they are based on the notion of reaction network. When individual species interact and form new species, and then you can place this reaction network into compartments or into different geometries, and as an end result, you simulate and find time courses of all those individual species. And it works fine as long as you really can define those species. But there are cases when you would like to look into more details. And for example, the previous slide was a reaction network for epidermal growth factor receptor signaling initial events, and it included just a couple of proteins, that adapter proteins that can bind to EGFR at the first steps, GRAP2 and CHIC. But if someone is interested in, say, SH2 profiling of EGFR, or in clustering of EGFR on membrane that can be enabled by multiple proteins, then you really would like to consider multiple domains that can serve as binding sites. And there are 9 such domains in EGFR, and multiple adapter proteins that can bind to it. And here, all this information is available, and even all the rate constants are available. But you end up with the notion that is called combinatorial complexity, explosion in the number of states. Because if you would like to consider all the different individual phosphosites that can be bound or unbound, then, and also if you have, say, Western blots experiments that can provide individual phosphorylation time courses for each of these phosphosites, so you would like to put it into a model, and you put each of these 9 sites into a model, and guess what will be the number of different modifications for receptor you have to consider. So there are 9 sites, each of them can be on or off, 2 to the 9 phosphosites for a single receptor. And then you would like to account for adapter protein, you add 1 binding partner per site, at least 1, and you end up with 3 to the 9 states of individual receptor. And then you add dimers, and you add trimers, and the number of individual species that potentially can participate in the reaction network is exploding, so that there is no sense to consider them. And this was an example today when the model included like 2,000 species and 11,000 reactions, and it still was a reaction network. So today I will tell you in more detail how this model was generated and how it was simulated. Not exactly this model, but the kind of models that are pretty large. So this is still, you can like find, approximate the number of possible species in a system. But there are some use cases when the number of possible molecular complexes in a system is just infinite. So actin filament is such a system when, if you have a supply of actins, then your chain can grow, and you really don't know ahead of time what will be the maximal length of actin filament. And if you include branching, it's becoming really intractable. You can do some approximation, but you really cannot enumerate them. Or like the favorite test case for polymerization is bivalent ligand, here on the bottom panel blue, and trivalent receptor. And this very simple system can lead to infinite number of different combinations and like huge topological structures. And in this case, we are not talking about whether all these structures can actually be realized in 3D or on a surface. For that, there are spring salad and there are other molecular dynamic tools. But just theoretically, how we can simulate those cases. Like, to get more detailed and less abstract, these are two cases that like the first is SH3 PRM nephrin interactions, and Oni talked briefly about it yesterday. So we have poly SH3, 3 SH3 domains. We have an WASP. I think you see my mouse, right? With these triangles being PRM domains. And then we have nephrin that are, so this blue vertical, in this case is cartactin, but it's generally the same as a nephrin receptor from functional point of view, that has multiple phosphosites that can bind to SH2, which is part of a NIC. So this is a NIC that has one SH2 and 3 SH3 domains. This is an WASP that has a multiple PRM domains. And this picture looks easy, but if you can guess, you can, like on these three sites, you can recruit another SH3s, and on free SH2s, you can recruit another nephrins. So this system becomes untractable. It's a large molecular aggregates. Or another system is when you have RNAs, and these RNAs have multiple sites, and then there are some proteins that can bind to those sites, and another multivalent scaffold protein that can bind to those sites and adapters, and it all glues these RNAs into large aggregates. So how can we model those? So at this point, I will ask for questions. Any questions? Anyone just can hear me? Because I don't see even any single face on.
We can hear you.
Okay, perfect. So I guess that we are all tired here at the third day. So in fact, please interrupt me. I don't expect with questions because I don't expect to have too many questions. So if you have some urgent, just feel free to ask it during my talk. So now, like one philosophical observation that mathematical modeling in biology started with systems like population dynamics, Lotka-Volterra, that was mentioned by Pedro, that was initially described just by differential equations. Say the change in the population of wolves is proportional to number of rabbits, and so on. Then, significantly later, people started to look at reaction networks. And those reaction networks, these are molecular species, interactions between them, and they were still solved by reducing to the previous level. Like people generated mathematical equations from reaction network and solved them. And in virtual cell and Copazi, you can look actually at differential equations behind reaction network. In virtual cell, this is a math model. And then the next level, when instead of considering reaction network, people started to consider properties of biological systems. And then these properties were used to build automatically reaction networks or do simulations. The same way as when you have a reaction network, you really shouldn't be a mathematician to write down the system of ODEs or PDEs. This is done by software. The same I will be talking today. The Biogen, biological network generator, or NFC, network-free simulator, they do the same job as a virtual cell does for reaction network or COPASI. You identify some properties of biological system, and then they build a network, and then they simulate the network. Or, I'll talk later, there is a different way to simulate. So we start with rule-based specification. So you have to understand that there is a specification and there is a simulation. And these are quite different issues. The same as in virtual cell, you can specify a model in physiology, and then you can simulate it differently using different applications. You can put it into compartments and simulate with ODs, you can put it in geometry and simulate with PDs, or you can do stochastic simulations for a small number of molecules. So, how do we do rule-based specification? This I will do now very quickly, and then we'll do into real demo. So we have molecules, and molecules have different sites, and sites serve as a binding to other molecules, or they also can have states. In this case, EGFR, it has EGFL, EGF-like domain for binding to ligand, transmembrane domain, and two phosphotyrosines can be on and off, or phosphorylated and unphosphorylated and phosphorylated. And then there are species, and species the same as in regular reaction network. It's just connected molecules. And then you have interactions. And the key with rule-based modeling, which kind of was a little bit covered yesterday in Spring Salad, that you have, like, interaction is local. You must have certain features of these biomolecules to enable interaction. For example, this is a notation for a biomolecule that is located on a membrane and that has a site, phosphosite 1092, being phosphorylated. And this is a feature of this molecule. We don't know anything else about it. It can be bound to ligand, it can be dimerized, it can be bound to another adapter proteins. We just know that phosphosite 1092 is phosphorylated. And these features, they define the set of individual species. So if we know that this is phosphosite being phosphorylated, then these are examples of different individual fully defined species. So it can be single phosphorylated receptor, double phosphorylated receptor, receptor monomer complex, and so on. And what actually rule-based modeling tells you is that there are certain features of molecules that you use to define interaction. So, and this feature, for example, if you have a ligand and receptor, and ligand and receptor have two unbound sites, then they can bind. And nothing else. It's like you talk in plain language. And then the software will, behind the scene, understand, okay, it means that if I have a ligand, and then I have one type of receptor, another type of receptor, third type of receptor, but they all are have the same features. They all located on the membrane, and they all have this site being bound. Then I can bind ligand to receptor and form a complex. So, assumptions of proteins modularity or like locality of interactions. And okay, so now let's switch to the interface, and I will do the quick demo of rule-based model specification. So we go new biomodel.
Excuse me, I have a question.
Yeah.
Yeah, so as you said in your slide, for example, if a ligand and a receptor have an unbound site, then they can bind and form a receptor ligand complex.
Yep.
Is this, let's say, deterministic, or is this stochastic?
I don't know yet. I didn't talk about numbers at all.
Okay.
So that's what I said. There is a declaration. It's the same as physiology in a virtual cell. You just define what may happen.
Okay, yeah.
So yeah, and then there are different ways to simulate it. Okay, so let's quickly go through the way to declare a model. So let's have, for example, we have a cytosol, we have a cytosolic membrane, we have a extracellular space, so we just define a cell with surrounded by a membrane, and we would like to do this EGF-EGFR interaction. So what we do, we have several molecules. So one molecule is EGFR, and another molecule is EGF. And what we know about those molecules, EGF should have a certain site to bind to receptor. So let's call this site like RB, receptor bound, or like, let's be consistent, it's called EGF-like receptor, EGF-like site. So EGFL. And what about receptor? Receptor, so far we are interested in it binding to a ligand, so we call it LB, maybe ligand binding site. And then we know that receptor is located on a membrane and can diffuse along the membrane. Oops. So let's call that this site that kind of attached to the membrane as TMD, stands for transmembrane domain. And then we will be interested in phosphorylation. So for phosphorylation, we introduce a site that is Y1068. And this site can be in two possible states. It can be unphosphorylated, and it can be phosphorylated. So this is declaration of two molecules. And now let's see how they interact. So we go to reactions and we say new rule. And now we would like to define that ligand binds to receptor. So where it happens, the same way as you do reaction network, you define that this interaction will happen on a membrane, because ligand should diffuse to membrane and receptor will stay on it. So in a membrane, you have a molecule EGF, and EGF actually is located in extracellular space. So another reactant is EGFR. So EGFR, and it is located on a membrane, CM. And the result is a complex. So you have a EGF, EGFR, and this complex is located on the membrane. So it's not the end, because what actually features of EGF and EGFR that will let them bind to each other. So this site, which has a question mark underneath, which means that it's just a site. It can be bounded, unbounded, but in order to bind to EGFR, it must be unbound. So we check it unbound. And this EGFR, it also, this site has to be unbound. And then the result is a binding between these two sites. Now we have to carefully think about biology. First of all, what else is required for this binding? Do we want it to be only when receptor is a monomeric, or do we allow ligand to bind also to receptor when it's in large clusters? let's say that we request that it only to monomers. So we limit our biological description to EGF binding only to monomer. Okay, we put site as unbound. And virtual cell is clever enough. It tells you that if in reactant EGFR was unbound, like monomeric, TMD was not connected to anything else, then it will stay the same when you have a product. And if you would like to do something like that, yeah, it will not let you do it because it was unbound. You cannot have that it's now bound to something. So this is just a snippet of what's happening in the system. And you had this receptor. It could be anywhere. It could be in a large complex. It can be phosphorylated, unphosphorylated, connected to something. This something can be connected to something else, and so on. But what is important is that this interaction is just forming a bond, binding of a ligand to receptor. So I will stop for a second and ask if this major principle is clear. And again, feel free to interrupt me. So this is one type of receptor of interaction. And let's go next. And let's say that now we have another rule on a membrane, and this would be dimerization. So dimerization means that we have two separate receptors. Two separate receptors. This plus means that those receptors are actually in two different molecular complexes. So they are not, in theory, you have molecules and they can be in a large cluster, like on different ends of huge receptor assembly. But this plus separates them as being differently in different complexes. And so dimerization is when these two receptors become in the same complex. And how? These transmembrane domains was unbound. And now it's becoming bound. And now you again have to think what is necessary for this interaction to take place. So if you think that it's just spontaneous, you can leave it this way and maybe put a pretty low rate. But I'm not talking yet about rates. Or you can say that we must have at least one ligand to drive these receptors into dimer. So for that, we have a has external bond. And that's enough, because by rule 1, this site can be bound only to EGF. So we don't need actually to say that EGFR is bound to EGF ligand. We just say that it's bound. And then we can say that no, actually we would like to have it that only two ligands can drive receptors into dimer. Or we can have like two different rules. So this one is a low probability when one ligand drives receptors into dimer. And then we duplicate this rule. And we say that now we have a higher probability that when both receptors and probability or rate of interaction when two receptors both bound to ligands, then they are complex, then they will form a dimer. So far we don't know what will happen eventually. We just define our biological knowledge. And then again, another simple rule in a membrane, because receptors are located in a membrane, would be dimerization. Oh, sorry, transphosphorylation. So what does it mean? Receptor, EGF receptor is a receptor tyrosine kinase. So it has a kinase domain that can phosphorylate adjacent, transphosphorylate adjacent receptor. So what it means is that we have a dimer, and if in this dimer if this is really dimer and this site was unphosphorylated, then it will become phosphorylated with a certain probability. Okay, and then virtual cell tells you an error, and why it is? Because you had these two receptors being connected as reactants, so they must continue to be connected.
Can I interrupt?
Yeah.
Yeah, very quick question. Specifically in this rule that you are establishing, one of the EGFR needs to be with a ligand in order to phosphorylate.
That's
so. Why are not we adding it as any one of the EGFRs as with the LB click on?
Exactly. So now you have a question: which of those EGFRs have to be with ligand? And this is like the rules are very detailed. So now you have several options. You can say that ligand must be here, and this is just site has a bond. You may have that ligand must be here. Or you can say that ligand just must be somewhere, but somewhere in the same complex. So, which for dimers means that if it's here, it must be connected either here or here. So then you define EGF, and those should be bound because this EGF is connected to this dimer, but you really don't know to which of those. So you see, these rules, so far we are defining a language. And this language is very detailed. And so far, it's even one-directional, because what may happen actually is that conditions for transphosphorylation and conditions for dephosphorylations would be different. So, for example, if you go and duplicate and dephosphorylation, then you don't need a ligand for dephosphorylation. And I would say even more, you don't need the second receptor in a dimer. What will happen is that you were phosphorylated, you become dephosphorylated. And what happens is that for dephosphorylation, you need this site to be unprotected. So phosphatase can approach it. So you go and you say this site is unbound. And this is an irreversible dephosphorylation reaction that just tells you that any ligand, once it is unprotected by anything and site is phosphorylated, this site can be approached by phosphatase and be dephosphorylated. And this one is also irreversible because you need to have both dimer and EGF. And so I defined it in this very complicated way. But in fact, rules are like when you start living in the world of rules, you start questioning any assumption. And now you understand that what actually will happen is that you don't need to the second receptor. You just, because if it is bound, then it's definitely bound to another receptor. So you have a kinase next to it. So it's enough to say that you have a receptor in a dimer and unphosphorylated site, so it becomes phosphorylated. And then you must have a EGF in this complex. So this, for the first time, can be tricky. Any questions?
Yeah, a very quick question. So based on that diagram that you just mentioned, that means that I can have HER2 instead of EGFR.
So far, no, but you're absolutely right, because what we can do new molecule, and you can do, for example, rename and have a HER2, or it's just simpler. Yeah, okay, so let's do HER2, and then this HER2 would have, again, just for simplicity, only transmembrane domain. And if now in your reactions you have another rule that will be just a dimerization of, dimerization of EGFR with HER2, then this phosphorylation rule will work also with HER2, because this transmembrane domain can be bound either to another EGFR via this interaction or to HER2 via this interaction. Correct?
Correct, yes, thank you.
Okay, so let's, this is a good example, so I can continue it, and then HER2, so this one was unbound, this was unbound, this must be bound, and the end result is formation of a bond. So we defined this initial set of rules, and now we are going into simulations. So in virtual cell, there is no way to simulate unless you add application. So let's add application. And there is a network freeze that I will mention a bit later, and there is deterministic. So deterministic, as I mentioned, there is a bionetgen, biological network generation, and this is deterministic process. You define the network that is equivalent to this set of rules, and this network is deterministically defined. So we go here, we go into application, we go into specifications, we go into network, and here there are certain limits. So you remember I told you about these 9 sites on a receptor can lead to 1,000 of different species for a single receptor. So to disallow this breakage, we define constraints. So I mean, let's just slowly show you how this network generation works. So the first iteration, apply, okay, and no, test run, and you will get an error. So an error is it's quite cryptic, but what it tells you is that you cannot start defining a network before you have something that will serve as seed species. So you have no species in your system. And how this network will expand? So you have to start with extracellular space. You have a species EGF, and then in membrane you have a species EGFR, and in membrane you have another species which is HER2, and it immediately pops you an error and starts flashing, because this is not a species, it's a collection of species, because species is a uniquely defined molecular entity. So this Y1068 should be either phosphorylated or unphosphorylated. So you start with unphosphorylated. Okay, now this red should disappear, and you can go and try again network generation. So let's see how the network generation goes. So test 1 iterations, go, and you have 4 species, but initially you had only 3 species in your system. So what is a new species? The new species is a complex of EGF and EGFR, because you had a ligand receptor and HER2, and you couldn't move forward anything dependent on formation of EGF and EGFR complex. Now let's see what will happen the next iteration. Test run. And now you have 7 species. So what are those 7 species? You started with 3 species, ligand receptor HER2. You got EGF and EGFR complex. Now this complex could recruit another EGFR, and this complex could recruit another, actually not this complex, but these 2 EGF and EGFR complexes could dimerize to form this one, and then this one could recruit HER2 to form this. And you can also check in reactions, and actually what I told you. The first reaction is this is how you would be in a biochemical soup. You mix 3 molecules and you see how they interact. So you first EGF binds EGFR, then it can recruit another EGFR, or 2 complexes can dimerize, or you have 2 complexes can dimerize. So what's the difference between here and here? Do I? EGF and EGFR. This is R1 and R10. So we'll see it. And R3. And R3 is recruitment of HER2. So what's R10? Okay, so it looks like, so R10 is, I started to tell you that we can increase the affinity if both of them are bound to molecules, to ligands. But I never actually defined how. Therefore, the network generates 2 identical reactions, but one of them would have a low affinity for this, and another one would have a higher affinity for EGF and EGFR complexes. So is it clear? Do you follow? Okay, so to make a story short.
Can you go back to the previous
Yeah.
part? Yeah. Okay. Why there is a question mark in reaction rule number R2?
Say it again.
Why there is a question mark on that specific
question mark? Because it can be either bound or unbound.
Okay, I see. So
so you see, in this case, this EGF, you will see it on the next iteration. Okay. So this phosphorylation will be enabled for anything, for either EGFR being in a complex with EGF, or EGFR being just in a complex with another EGFR that is bound to EGF. So let's go specification.
Michael?
Yep.
But there, if you go back again, there was a triangle with an exclamation mark.
Okay,
there.
Yeah.
What
so let's
that?
see. Yeah, this is a good point. Let's see, warning.
That was my question. I'm sorry.
Okay, yeah. So found disjoint unit. So this is a warning. It's not an error, but generally, if you have this kind of interaction, it may cause problems, because Binagen cannot directly traverse from here to here, and it can go into, say, think about it as a huge aggregate, and this EGF is somewhere on the other end of this aggregate. So it can be both biologically not correct and computationally intensive. So in this case, we raise a warning. And we also another warning that maximum number of iterations is insufficient, which is also correct because this system is still truncated. So let's see, and we go to this like put 12 iterations, and then there are other types of constraints. We can have molecule, species, so test run, and so the simple system ended up with 13 interaction species and 21 interactions, and this is all that may happen. And you can now create this biomodel, and this is how BioNetGen works. You can either simulate it within the existing model, or you just created a model and now you can place it, you can assign to individual species individual diffusion constants, you can put it into complicated geometry and so on. So now we really have not much time. So we so far covered BioNetGen, rule-based model generation that tells you we have initial species, in this case it was ligand and two isoforms of a receptor, and we have a set of reaction rules, which was just ligand binding, two dimerizations, and phosphorylation. And then we went through this iteration 1, iteration 2, when this system was, every time these possible reaction rules applied to the species, and we got more and more species and reactions. And at some point, we got the complete reaction network. So those rules can be still applied within this complete reaction network, but nothing new would be generated. So it's useful when your system is pretty, like is finite. It gives you the full control of what you're doing. You have these rules and you know that you generate what you need. So this is BioNetGen when have input network, so you go through the plain way. Now, sometimes, as I told you in use cases, your system will be infinite. So in this case, there is no way to generate the network. And what we do in this case? So I didn't cover observables. Observables is a very important feature of rule-based modeling, because even if you have 13 species, or if you have 1300 species, then going through each of them and making sense of, say, this is 13 species. So you really, those are called microscopic species, and you really don't care about time course of this compared to the time course of this. They're different just as you see in the composition of, in like binding between sites. So what you're really interested is in certain observations. And those observations, like the total number of receptors in a system. Okay, in your system, it just should stay constant. It's a mass conservation. The total number of EGFs, the total number of HER2. By the way, do you see? Yeah. Now, what you really could be interested is homodimers. So these homodimers would be EGFR and EGFR. And you can interested, and then let's do, yeah, it's enough. And then new observable would be heterodimer. And heterodimer would be EGFR, HER2. So this is what you would like, yeah, to monitor. And both by energy, but like rule-based model and specification gives you a way to do it. So you go back to specifications, edit test constraints, turn run. So you have a 13 species, and in the 13 species, you have a heterodimer, and heterodimer now corresponds to 2 different species. You see they're different in this. Phosphosite can be either phosphorylated or unphosphorylated. And homodimers are also 2 species. Oh, homodimers actually very many, because you have receptors with dimer with 1 ligand, dimer with 2 ligands, and then different phosphor forms of dimer. So you see you have a lot of different homodimers, but all of them, they have the same in common. They have 2 receptors. And this is what you're interested. This is what you would like to match to experiments. So Binagen generates these homodimers, and then you can, when you do simulations, you can get them. But what NFSIM does, network-free simulation, it bypasses all these reaction networks, and it immediately gives you the time courses for observables. But this is stochastic. So when we talked with about Binagen, I never dealt with numbers because it's a deterministic way to define a model. NFSIM is a stochastic modeling. You need to have an initial set of initial numbers. So here I will stop with my demo and just will open one of the models. And for simplicity, I will start this rule-based GFR tutorial, which is single compartmental. Everything with multiple compartments take longer. So we can do this. So this is expanded model of what I started to do, but without HER2. Just homodimers, and then grab 2 and Chic being able to bind to phosphorylated sites, and we got 2 sites on a receptor. So one way is to do deterministic model. So we click to it on a blue button, and we expand, or in our terminology, it's flattening the set of rules into reaction network. So it got 60, let's see how many, 87, I think that it goes above 100, 106 species. And now you got this model with 106 species, and you just can do with it whatever you want. You can also, within virtual cell, just place it into multiple compartments. And this is, you can get so-called generated species. So you can get a time course for each of these individual species. But what you're interested in observables. So we defined the phosphorylation for one tyrosine, phosphorylation for another tyrosine, and this is what this model gives you.
I'm sorry, I got lost here. So what are the rules for interaction? You know, the issues, you have all these species at the beginning, you allow them to interact with each other, but, you know, are these interactions, you know, the probability of interaction between each other is what, 1, or can you elaborate on that, please?
Yeah. So I didn't mention parameters. When I define the rule of interaction, for example, this is ligand binding, you treat it the same way as it would be individual reaction. So when you define ligand binding to receptor, you have kinetics, and you have a forward rate and reverse rate for mass action.
Okay, I see. So you already introduced all these All the coefficients of interactions are already provided.
Yeah, to do time courses, you need to define rates. And the trick is that this reaction rule actually corresponds to very many individual reactions when all these can be phosphorylated, unphosphorylated, bound to adaptive proteins. So all these individual reactions, they have exactly the same kinetics. All this Kf and Kr are the same. And then you definitely need to have initial conditions, and you go here to specifications and you define the initial conditions. So you can generate the network without numbers, but to do time courses, you need to have certain parameterization. But then you can also do, and this network I didn't show you, but we already had a certain like maximum number of iterations, number of max molecules per species to control how the network grows. So it's 684 reactions, pretty large model. But there is a network-free simulation. And in a network-free simulation, we don't deal with any of the network parameters because it doesn't generate the network. So let's run it again. Now I'm running this network free. And what it does, there is no generated species. These are initial species that were in the model. And these are observables. So we can compare, say, Y2 to Y2 here. So we get the same time course for observables. But in the network-free simulation, there is no way to look at the network. There is nowhere in this model when you run it, you know which individual species are generated. And the reason is, let's look at this rule-based specification. So in the middle there is a declaration that A and B, if two sides are free, then they can bind and form a bond. And then if B and C, there is a C side and B side, and if these sides are free, they can bind and form bonds. In Binagen, you use these two rules to generate all the different interactions, A plus B, A plus BC, B plus C, and so on. So, and then given this reaction network, you can parameterize it and start simulation. What NFSim does is similar to spring salad that was discussed yesterday. You have initial distribution. You have a certain number of molecules B, certain number of molecules A, certain number of molecules C's, and all of them just like non-spatially, you don't have any diffusion. They can participate in these rules. So what network-free does, it just randomly, according to propensity of this interaction, finds A with a free side, finds B with a free side, and build a bond. And then if there is a reversible, then it finds this complex, like this one, and it breaks a bond. And then if there is another rule for B binding to C, so it just choosing some molecules B and say C here, and it gets a bond. So this is a regular stochastic process that was discussed again yesterday, which means that you have those agents and you choose based on the propensities of reaction rules, which reaction rule will fire first. So you have in this case 4 rules: irreversible binding, irreversible unbinding, irreversible binding BC, and irreversible unbinding of a breaking of a bond between BC. So according to propensity, which of these rules is fired first? You select, for example, that A and B will form a bond with the highest probability, and you build a bond. In this case, you never actually know how all these are connected all together, because it's tricky. If you remember this huge cartoon, how can you find if you mix all these complexes, if it will be the same complex or not? But what you have always. So what's an observable? Observable, you remember, let's go here. Observable is, for example, this is a dimer. It's a receptor that is bound to something. And to find number of EGFRs in dimers is very easy. You don't need to know how many different species. You just go through this cartoon and you see, for example, how many A's are in a complex with B. This A has a bond, this A has a bond, this A has a bond. So there are 3 A's that are in a dimer. How many C's are in a complex with B? 1, 2, 3. How many B's are connected at the same time to A and C? Just 1. This is the essence of network-free simulation. You don't know the network of interactions. You just know the snapshot of what is a connectivity and different states of molecules in your system. So I have 2 minutes left, and I just will tell you 2 more features that we have in virtual cell, and those features are unavailable in so both Binagen and NFSIM exist as a standalone. Here I crossed nfsim.org, although it's the first site that comes when you search for NFSIM. Actually, it has outdated version, and on the site binagen.org, there is a version of NFSIM with some bugs being fixed. But anyway, both of them exist as a standalone, and both of them use scripting language which calls Binagen language. And this Binagen language is something that we can import and export. So the model that is done in a virtual cell can be exported into in a standalone Binagen and NFSIM, and model done with those tools can be imported into the virtual cell. We have a much better user interface with all these errors and warnings. If you need to design a model, I highly recommend using virtual cell. Standalone tools, they have more features. You can do some of the kinetic laws that are unavailable in virtual cell. For example, Michaelis mentioned. So you really would like to mix and match. You can start in virtual cell and continue with standalone tool. What we are unique, we have a spatial modeling for both biological network generation and network-free simulation. And in this spatial modeling, we can anchor the molecules to specific compartment. So I didn't mention it in my test case, but when you got species, you can say, not species, molecules. So this molecule EGFR can be actually located only on cytosolic membrane, and this red, so everything red in virtual cell means a mistake or error. And EGF can be located either in extracellular or cytosolic membrane, and HER2 can be located only in cytosolic membrane. And then if you have, for example, a rule of translocation of HER2 into endosome, then this rule will not be applied unless you add another compartment, which is endosome, and you enable this molecule to be located also in endosome. And then we have a visualization that will let you, not this one, will let you select one of the complexes and see all the different interactions this complex participates. You also can switch to the so-called molecular configuration name. So in this case, you see that EGFR molecule, and you can see all the rules where this molecule participate. So you can explore your set of rules and resultant network in many convenient ways. So I think that I will stop here.
One quick question, Michael.
Yeah.
Very quickly. Go back to your previous slide. The network that you just the previous.
You want a slide
the
which
software. Just go back.
Yep.
That specific reaction model that you have there. Can you compare it with the cytoscape curated model and find which ones are observable in biological experiments and which ones are not?
There is a SciSBML plugin in Cytoscape, and this is the only plugin that actually works with species. So we generally incompatible with Cytoscape, meaning that we deal with modeling formats and Cytoscape deals with just data representation where they don't look inside molecules.
But in Cytoscape, you observe, they provide you with the resulting observables in experiments. So don't you think that you should compare the resulting species from one to another?
In theory, yes. Basically, so this is a question about how you can fit your model to observables. And the answer is yes. Observable is just a function. Observable is, so I mentioned that observable is the set of species, but I was not correct, because observable is a sum of all species that have these features. So if you have a dimers, then observable, so let's go here, specification, network, observable. So this is so this is, for example, observable corresponds to the total phosphorylation of EGFR on site Y1. And if you look, there is a multiplicity. So what does it mean? Species, it started, okay. Species that has a single molecule, it has a multiplicity 1. So you count the number of these, the concentration or population number of these complexes as one, because it has only one receptor. But this dimer, it has 2 receptors, both of them site Y1 phosphorylated. So you count the number of those complexes or concentration of these complexes twice, because you would like to match it to the total number of phosphogroups. So yes, if there are certain observables from experiments, you can use them for fitting, because this is just a function that is defined in virtual cell in mass model, and you can use it. Okay. So.
There was the question in the chat.
Yeah. Oh, I didn't. Sorry, I couldn't. Yeah, but Stefan, sorry that I took 5 of your minutes. So please go ahead.
No, that's fine. No problem at all.
Yeah.
Okay.
Genevieve, that question is not really clear.
What Jan did you say?
Oh, so I was just curious.
There's a question in the chat.
Yeah, in terms of the spatial compartmentalizations, is it possible to then couple that with a diffusion gradient for the different, say, ligands within a given compartment?
Unfortunately, if you define it within rule-based model, no. Because we don't have a rule how to define diffusion for complexes.
Right, that's what I was wondering, if there was a way to sort of like hybridize the two modeling techniques, or if they were still very much distinct. No. Okay, thank you very much.
You're
welcome. I could just add to that spring salad, which obviously is only good for much smaller models than the kind of models that you can build with rule-based modeling and V-cell, but with spring salad, it automatically will adjust the diffusion coefficient as a complex grows. It's sort of built into the algorithm. So that would work if the model is small enough to be buildable within spring salad.
Yes, unfortunately, probably not. But thank you.
Well, I think you might be able to take that generated model, import that back, and then add fields or modify the kinetics.
Yes, once you have a model, however big it is, you can do whatever you want with it.
Right.